In August of 2024, NASA suddenly shut down one data channel of the Juno-Jupiter probe. The official explanation was a technical malfunction, but 3 months later, the journal Nature published a paper with a title that was only 4 words: Jupiter core is melting. What does that mean? A gas giant 11 times larger than Earth. Its heart is slowly fading away. Even more surprising, scientists discovered the melting speed of Jupiter's core is 1,000 times faster than predicted. You are probably asking, what does Jupiter's core have to do with me? Listen carefully and it will make sense. Jupiter plays a role in the solar system far beyond being just a planet. It acts as a cosmic cleaner. Every year its massive gravity helps Earth intercept tens of thousands of potentially dangerous asteroids. Without Jupiter, Earth's risk of impacts would be far higher. But now if Jupiter's core undergoes major internal changes, will the stability of its gravitational field be affected? And could that alter its role as Earth's protector? What puzzles scientists even more is the discovery of a substance that only forms under extreme conditions: liquid metallic hydrogen. This material requires roughly 5 million atmospheres of pressure to exist, thousands of times the pressure of Earth's deepest ocean trench. Under such pressure, hydrogen atoms are compressed until their electrons break free, turning hydrogen into a metal that can both conduct electricity and flow like a liquid. But what truly confused scientists was data sent back by Juno in 2022. The data showed that the boundary of Jupiter's core is not sharp or well-defined. Instead, it gradually fades. What does that imply? It suggests Jupiter's core may not be a dense solid sphere as traditionally believed, but rather a high-density region slowly mixing with surrounding material like a sugar cube dissolving in water. So what is wearing down Jupiter's core? The answer may be unexpected: Jupiter itself. Jupiter releases more internal heat every day than it absorbs from the sun. It behaves like a massive heat engine, constantly consuming and reshaping its internal energy and material. Scientists estimate, if these core changes continue and intensify, subtle long-term shifts in its gravitational field may someday, far beyond the scale of human civilization, affect the dynamics of the entire solar system. So here is the question: if one of the solar system's gravitational anchors changes internally, what challenges does this pose to our understanding of planetary evolution and system stability? Don't rush, the answer is stranger than you expect, because in 2025, a quiet scientific earthquake took place. A research team at Durham University used supercomputers to simulate hundreds of planetary formation scenarios and reached a conclusion that overturned textbooks: Jupiter's heart may not have been fully solid from the very beginning. Wait a second, this is completely different from what we were taught. Traditional theory says gas giants form like rolling snowballs. First a solid rocky or icy core forms, then gravity pulls in surrounding gas and dust, growing larger and larger. Earth formed this way, Mars did too, so Jupiter should have done the same. But Juno's data was like a bucket of cold water, shaking a model that had lasted for decades. You might ask, how do scientists know what Jupiter's interior looks like? They never drilled inside it. That brings us to an elegant method: gravitational CT scanning. Each time Juno flies close to Jupiter's cloud tops, it sends ultra-precise radio signals back to Earth. When a region inside Jupiter is denser and has stronger gravity, it slightly accelerates the spacecraft, causing the signal frequency to increase. On the other hand, weaker gravity lowers the signal frequency. Using this method, scientists combined data from dozens of flybys to reconstruct a detailed 3-dimensional map of Jupiter's interior. What this map revealed caught everyone off guard. Jupiter's core is not a sharply defined solid core. It looks more like an unstirred thick fluid, heavy elements mixed with lighter hydrogen and helium, gradually thinning from the center outward, with no clear dividing line. Even more striking, this fuzzy core region is enormous, occupying nearly half of Jupiter's radius, equivalent to digging downward more than 3 Earth diameters, and still remaining within the gradient core zone. This discovery triggered intense debate. Some scientists proposed a dramatic idea: the cosmic collision theory. They suggest that shortly after Jupiter formed about 4.6 billion years ago, it may have had a normal solid core, but at some point, a protoplanet roughly 10 times Earth's mass slammed into the young Jupiter. This massive impact may have shattered the core, mixing its fragments violently with the surrounding gas layers, producing the fuzzy structure we observe today. The story sounds reasonable, but unfortunately, supercomputer simulations in 2025 ruled it out. Researchers tested hundreds of impact angle speeds and object sizes, and found a fatal flaw. While impacts can disrupt the core initially, over time gravity would cause heavier material to sink back toward the center like sand settling in water, reforming a new core with relatively clear boundaries. In other words, a single violent collision cannot maintain an extremely fuzzy core for billions of years. That path seems unlikely. So what is the real answer? Scientists turned to Jupiter's neighbor Saturn. By analyzing Cassini data and subtle wave patterns in Saturn's rings, they uncovered a striking fact: Saturn's core is likely fuzzy as well. This changes everything. If only Jupiter were like this, it could be a rare accident accident. But if Saturn shares the same trait, then fuzzy cores may not be anomalies, but a common or even standard internal structure of gas giants. The latest models suggest Jupiter's fuzzy core likely formed naturally within its first few million years. Picture the scene 4.6 billion years ago. The sun had just ignited. The protoplanetary disk was filled with gas dust and ice. Young Jupiter grew rapidly like a giant in a growth spurt, greedily pulling in heavy elements, while also swallowing massive amounts of hydrogen and helium. It grew too fast too violently. The accretion process was chaotic. Heavy material and light gas were intensely mixed as they plunged inward, leaving no time for orderly layering. Light material rose. Everything blended together. In the end, Jupiter became a massive planet with gradual transitions from core to surface. But this leads to another mystery. Jupiter has the strongest magnetic field of any planet, nearly 20,000 times stronger than Earth's. Its magnetosphere forms a gigantic shield, extending almost to Saturn's orbit. Such a powerful magnetic field usually requires intense convection of electrically conductive fluids deep inside a planet. Yet Juno's data suggests that Jupiter's fuzzy deep interior may actually be relatively stable, with weaker convection. How can a calm deep region support such an extreme global magnetic field? It is a paradox like still water, hiding the energy that drives massive ocean currents. This contradiction remains one of the deepest mysteries in planetary science. At this point you may ask, why does understanding Jupiter's fuzzy core matter to us? What difference does it make? The answer is it matters a great deal. First, this discovery directly challenges and enriches our core theories of planet formation. If fuzzy cores are a natural outcome for Jupiter and Saturn, then hundreds of millions of similar gas giants in the galaxy may share equally complex internal structures. This means our simplified layered cake models of planets may need fundamental revision. Second, the state of Jupiter's core affects its long-term evolution, heat flow and gravity stability, while the effects on Earth are negligible on human timescales, practically invisible. Over millions or billions of years, even tiny gravitational changes can trigger butterfly effects. An asteroid Jupiter deflects today could be the one that would have reached Earth tomorrow. Next-generation missions arriving in the Jupiter system in the 2030s will carry more advanced instruments. They will not only study Jupiter itself, but focus closely on its icy moons Europa, Ganymede and Callisto. At that time, we may come closer to answering one of humanity's oldest questions. Are we alone in the universe?